Yeah, so hello guys. So this is going to be the solution for question 1 and sorry, for question 1B, yes. So and the first question here, which is question 1BI, says what type of finite state machine model is this? So as we all know, there are two finite states machine model. We have the Moore model and we have the Mealy model. And one way you can differentiate them is the way they are drawn, most especially the output part of it. So normally, if you have a model or if you have a state diagram like this, we have 1 of 0, 0 of 1. So what this means is that this one inside the circle is our state, this one here is our input, this one here is our output. So this line is indicating that when our input is 1, the output is 0, and the next state is let's say we have a B here. So this line here means when we are at state A and the input is 1, the next state is B and the output is 0. So let's say if we are at state A and the input is 1, the next state will be B and the output will be 0. So this is the output here. So the other line here, we can put a C here. It's saying that when we are state A and the input is 0, the next state will be C and the output will be 1. And this kind of model that you draw this way, that you draw the input over the output, the input over the output, is called a Mealy. How is that spelled? Mealy model. So the other side kind of model is the one in which you are going to draw like this. So for this one, you notice we don't really have the input over the output here, and we have two elements inside the circle itself. So this type of model is independent of the output. What we have inside, the input is like the output is independent of the input. Yes. So the output of this kind of system, the output is independent of the input. So irrespective of the input that we have, our output, which is this one, will always be 0. So this one is our input, this A is our state, this 0 here is our output. So this will be B, maybe B over 1, C over 0. So in this kind of model, you already have the outputs inside the circle, and this model is called Moore model. So the first part of this question that we have here says, which kind of model is this? That's 1B high. Based on what I just explained, we have a single state, we have a single value inside the circle, which is B. We have when the input is 1, the output is 0. When the input is 0, the output is 1. So this one resembles what we have here, and this is the type of which model. This is the type. This is a Mealy model. Okay. So the second part of the question says we should prepare the state transition table for the given finite state machine. So to what is meant by the transition table is a table that will include the present state, the next state, and the output. So for this one now, we have the present state has A, B, C, D, and E. So the next states that we have when x equals to 0 and when x equals to 1. And we have outputs when x equals to 0 and when x equals to 1. So how do we now fill this table? So given are the present states, this one here is the present state, this is the next state. So what's actually even meant by present state and next state? So present state is the state you are referring to at a particular moment. For instance, if you are referring to state D will be your present state, and wherever the arrow of state D goes to is going to be your next state. For instance, the arrow of state D goes to E when the input is 0, so E is the next state when the input is 0. The arrow of state D goes to C when the input is 1, and that's basically going to be the next state, C. So now, based on what we have here, they said our present state is A. This is A. When x equals to 0, that's this line here. This is when the input is equals to 0, because x is our input. The next state is what? The next state is C. So we have C here. And what's the output? The output is 0. The output for this is 0. So when we also have state A and the input is 1, the next state is what? The next state is B. So the next state is going to be B and the output is going to be 0. You do the same thing for state B. This is state B. So when you are at state B and the input is 0, x equals to 0, when is that? So this is it. X equals to 0. The next state is C and the output is 1. When you are state B and the next state is 1, the output is going to be 0. The next state is D, sorry, and the output is going to be 0. When you are state C, which is this, and the input is 0, the next state is A and the output is 0. When you are state C and the input is 1, this is the input here, the next state is E and the output is 0. When you are state D and the input is 0, the next state is E. The next state is E and the output is 0. When you are state D and the input is 1, state D, the input is 1, the next state is C and the output is going to be 0. So similarly, when you are state E, where's state E? Yeah, the input is 0. When you are state E and the input is 0, the next state is A and the output is 1. When you are state E and the input is 1, the next state is D and the output is 0. So this one we have here is called the state transition table. Now after that, they said we should make use of implication chart methods to reduce the number of states in the given finite states machine to the barest minimum and draw the reduced state transition diagram. So what we are trying to do now is to find the equivalent states here and reduce them by using implication charts. If you are trying to use implication charts, the first thing you do is start with, we have A to E. So along the horizontal, this is going to be 1I. So along your horizontal, along your vertical, you have B, C, D, E, and along your horizontal you have A, B, C, D. So you notice this one is missing A and this one here is missing E. So what you do now is draw this shape that we're going to draw now. So now anytime you are talking about something is equivalent, this is going to be equivalent. If you have two states, we have A, which is our present state, our next state is CB, and B, our next state is CD, and our output is 0, 1, 1, 0. Now for these two states A and B to be equivalent, so for A and B to be equivalent, this next state must be the same. That is, their next states must be the same. Now if you are saying their next state is going to be the same, if you notice they actually have two next states. What it basically means is that A will be equivalent to B if and only if this state is the same, C is equals to C, which is true, and B equals to D. That is, C must be equals to C and B must also be equals to D. But that's not the only thing. Also, their output must be the same. So that's the only time two states are going to be equivalent. So, and in that case, when you notice that the B and D are the same, C and C are the same, and their output is also the same, in that case you can always replace B with A or A with B. But in this case now we have 0, 1 in the output, 1, 0 in the input. 0, 1 is not equals to 1, 0, then A is not equals to B. But at in bin you have 0, 0 here and 0, 0 here. In that case, since we notice that 0, 0 is the same thing as 0, 0 and C is equals to C, then these two states will be equal if B is equals to D. So now we just need to prove that B is equals to D. Then if we prove that B equals to D, then we can say A is equals to B. So that's the whole idea of transition of equivalency. So now, how do you now put all of this in the implication chart? Now you pick these rows. First off, before you even do anything, you look at the rows, like you look at the rows that you have, and anywhere you notice that their output are not the same, you can mark them that they are not going to be the same. So if you look at A and B are never going to be the same because their output are not the same, 0, 0, 1, 0. Then A and B, they can never be the same. A and C have the same output, 0, 0, 0, 0. Then there is a possibility that they can be the same. You just leave the box. This is box A and C. Then A and D also 0, 0, 0, 0. So there's a possibility that A and D might also be the same. So you just leave it as it is. And the last one 0, 0, 1, 0. A and E, because they have different outputs, they can never be the same, so you cross it out. You do the same thing for B, C, and D. So let's start with B. For B now, we have B and C. Is B and C equivalent? No, we have 1, 0, 0, 1. So it's not possible for them to be equivalent, so you cross it out. So the next thing is B and D. Let's see, B and D. 1, 0, 0, 0. Also, it's not possible for them to be equivalent because the output are not the same. And now we have BE, 1, 0, 1, 0. So we can leave this one as it is, as it's possible for them to be equivalent. We just have to check the next states. Now the next one is C 0 0, that's CD 0 0 0 0. So that's possible. 0 0 1 0 for CE, that's not possible. C and E are not possible. So the next one is D. D and E are not possible because we have 0 0 1 0. So they are not possible. So now after you've marked those that are not possible as a result of the outputs, you now have to check the next state. So now for A and C, let's say A and C will be equivalent if A is equals to C. This is one here. This is A and C. The next state of A and C is this CA. So you can say these two states are going to be equivalent if A is equals to C and if B is equals to E, and similarly AD, where is AD? This is AD. AD will be equivalent if C is equals to E, and B equals to C, and B equals to C. So that's for this row. Now you do the same thing for this row. So BE, so BE will be equivalent if C equals to A or A equals to C. So let's use A equals to C. So always start with the small, or let me say the first alphabet that comes alphabetically, if that's correct. So also for B and E to be equivalent, D and D have to be the same. D and D. The next thing is to do for C. For C and D to be equivalent, A and E must be the same, AE, and EC must be the same, or CE must be the same. So we've covered all available spots. So the next thing you're going to do is you look at all of these states here, or all of this box here. If what's in the box is equal to the coordinate of that box, you can actually remove just that part. For instance, the coordinate of this box, so of that box, we have the box like this, and we have AC. So A, C, B, E. So the coordinate of this box is AC, and we also have AC inside, so we are safe to remove AC. So in that case, we are free to remove AC because that's the coordinate of the box. That's more like redundant. Which one again do we have as the coordinate of the box? We have CE, BC, AC, DD, we have AE. So we have AE, we have CE. So let me check for CD again. Yeah, CEAE now. So now the next thing you need to remove is the box in which they have values like DD, AA, where the two values are the same. So because these are actually the values in which they have DD, AA, CC, BB, EE, all these ones are already equivalent, so we can actually remove that one from it also. So now if you look at it, we only have DD here. So as a result of the DD that we can remove the DD. So after removing this one, the next thing we need to do now is check each of those boxes again to see if the coordinate inside the box is cancelled. For instance, now in this coordinate of AC we have BE. You are now going to go and look for the coordinate of BE and see if it's cancelled. We notice BE is still alive, which is AC. Then you go to the next one, CE. If you look at CE, this is CE. You notice that we have actually cancelled CE. So then CE are not equivalent because that's the reason we cancelled it. So we can say that AD are not equivalent since CE are not equivalent. So we can cancel AD. So the next thing is AC. If you look at AC is actually still okay. We have something inside it. AE, what about AE? So if you notice AE, we have actually cancelled AE. So we are going to cancel this one also. So and that's going to be all. So now you are going to check again one more time. B is still alive. AC is still alive. So that's going to be our redundant state. So now, when you are trying to pick the states that are equivalent, you don't pick what's inside the box, you pick the coordinate of that box. So for instance, the box that we have here, we have a box here that contains BE that has a coordinate of AC. So you don't pick BE as equivalent yet, you just pick the coordinate of that box. That's going to be AC. So you are free to say that A is equivalent to C because that box is alive. So similarly, we can say A is equivalent to C. Now the second box here contains AC and the coordinate is BE. So we can also say that B is equivalent to E. So that anytime we see A, we can replace it with C. Anytime we see B, we can replace it with E. Or anytime we see C, we can replace it with A. Anytime we see E, we can replace it with B. So and that's what we so now we're asked to draw the resulting transition table. So now the resulting transition table, we are going to get it from here. So from here, we note what we are going to do now is that anywhere we see C, we replace it with A. Anywhere we see C, we replace it with A. So this particular table here, this is C, we replace it with A. And anywhere we see E, we replace it with B. So here we are going to replace it with B. And let's say we have a C here, we replace it with A. We have a C here, we replace it with A. We have a C here, we replace it with A. And we said anywhere we see E also, we are going to replace it with B. So this is B, and that's all. So the reduced table that we are going to have, that's going to be the fourth part. We have present state, the next state x equals to 0, s equals to 1. We have A, B, and D, and that's going to be A, B. We have outputs of x equals to 0, s equals to 1. So we have AB, we have AD here, and we have BA. So AB, AD, BA, and 0, 0, 1, 0, 0, 0. So this is our reduced state. Now, so the next question says we should encode the states. So let me pause this one first and